So he got his master's in from Sony Buffalo and professor Barnett and on the network projects. And actually, I met with Ben like 3 years ago in Sunbelt a couple of times and watched his demo on the previous version of this software called Jacob's Ladder. It's pretty impressive software, and it can handle. At that time, Ben told me we can handle like 1 million nodes in the network and do animation, even hear the sound of the network. So we'll have a chance to see the latest progress of that software. And also for today's this Sonic series talks, we sent emails and to multiple places, and people may join. I think probably the one is Brooke online. I saw her name on the VW list. So basically, people may join in the middle of talk, but we can keep going. Okay, so Ben, now it's your time, and get started.
Thank you very much. As you said, my name is Benjamin Elbirt. I'm currently working out of my own home on software, and this is a presentation of what our latest software is, which is two pieces, a program called Matrix Coordinates and a program called the Elbirt Technologies Visualizer. First, I would like to thank Northwestern University for hosting, Dr. Contractor for the invitation, everyone who's helped set things up, and of course all the people who gave me my data. This presentation is going to start with a quick keyword reference so that we're all talking on the same language. From there, I plan on talking about how you can obtain the software, which is free. Then I will talk about the matrix creation software. This is what's going to take your raw data and put it into something you can visualize. And I'll warn you now, the first section, conversion of raw data, and the second section about Procrustes rotation is about as mathematical as this is going to get. After that, it's going to get more graphical and more fun. From there, we'll actually talk a little bit about the visualizer. I'll show you a brief interface graphic. We'll talk about the examples, and then we'll actually get right into it. And then finally, I'll show you a bibliography, and we'll have some Q&A. Okay, for the keyword quickie. There are a lot of different ways to refer to the objects that we deal with as our data. Tokens are a common term in text analysis for Java, objects, entities, elements. These are all the things we're studying. I will use these terms interchangeably. Edge and relation. For those of you who know network analysis, which this software is mainly based around, we talk about the relationship among the objects, and we refer to the values as edges or relations. Finally, sets, systems, matrices, again, all different ways of referring to our data sets. And I will use them interchangeably. Okay, to obtain the software. This is my website, and the software is absolutely free. You're welcome to use it, download it. It comes with documentation, and I'm available for questions via email. All it requires is the latest Java runtime and a Windows operating system. To install it, you're going to unzip the file you download and then just run the jar file, which will start a full installation process so there's no more copying and pasting. It even includes icons for shortcuts on your desktop. Finally, just a couple notes. I've had experience with some people who helped me test. Every so often, we would run into someone who had a 64-bit operating system with 32-bit Java installed, and it will not run if you download the 64-bit version. So you got to make sure that your Java installation matches your operating system. Finally, I don't make any changes to your system. I install to a single directory, which is mentioned in the documentation, and you can just delete the directory if you ever want to remove the software from your system. I do not play with registry settings. Okay, so now we're going to talk a little bit about the matrix coordinates program. This program is really going to be the bedrock to getting to the visualizer as quickly as possible. Now this program is going to take your raw data and it's going to create, through structural equivalence modeling, a monthly dimensionally scaled space, a coordinate space. Multidimensional scaling is a form of analytics that you can look up. There's a lot of literature on, and it's a great way of creating coordinate systems out of distance information. It's used a lot with space, and we've used it in cognitive structures. There's really a lot of different ways to apply it that can turn your data into a coordinate system. Now, our input data, it varies a lot. In the case of social networks, we can have directed and symmetrical. We can have distances, or we can have strength relations or co-occurrence relations. I mean, there's a real massive amount of ways we represent data. And then in some rare cases, we even have negative values. Now, for MDS to work, it needs a symmetrical matrix of distances. This is the only way it can convert into coordinates. In order to do that, I use a technology, or really a mathematical function, called structural equivalence. Structural equivalence uses the Pythagorean theorem to create a distance out of the matrix of information by comparing the rows and the columns of each node to each other node and having the differences add up into a distance. We use the squared difference between values, which handles the plus and the minus issue. And of course, the final value is a distance, which is exactly what we want. It also looks at both the row and the column values for each of your data objects. This is important because it's not just considering each element of the matrix, it's actually considering the structural position of each object in the matrix as it relates to other objects. So you're really taking into account both the full row and the full column, which in turn allows us to deal with direct networks. And of course, a distance is symmetrical, so our end result is a symmetrical distance matrix, although we started with something completely different. Now, for a second, I'm going to stop and see if anyone needs me to go through that again, because it's a little bit rushed in the mathematics, or if you guys are okay. Is anybody there?
Yes, we don't have questions. Actually, I muted.
Okay.
If nobody is speaking, just keep it muted.
Okay, no problem. I just wasn't sure.
Okay.
Okay, so what matrix of coordinates is basically going to do is it's going to compare each object structurally to each other object, determine how different they are, and represent those differences as distances. Once that final matrix is fed into the MDS algorithm, it returns a series of coordinates, and those coordinates are what we're going to visualize. Now, one of the fallbacks of multidimensional scaling, which is right here, okay, is that MDS doesn't normally look at previous iterations of generation. So if you have a time series data set, for example, you looked at Facebook relationships every day for 30 days, so you have 30 data sets. Each data set, when it's run through multidimensional scaling, is run independent of all other data sets. Now, in a time series, this is bad because it's going to find the best fit, and the best fit isn't always going to match to the previous set. Now, what do I mean by that? Imagine a gyroscope, okay? Now, a gyroscope looks the same no matter how you spin it. When MDS generates the coordinates, it in a sense, rotates them around the center to find the best way to match everything up. When I look at one point in time to the next, what it can create is, for example, a flip on the axis. So in one time point, it's on the left side, and at one point, it's on the right side, which is really bad. Now, I'm going to show you graphically what I'm talking about as soon as we're done with the Procrustes, but it's important to realize that this rotation is very important, especially when you're doing longitudinal studies. Okay, so what I did is I used a custom Procrustes solution, which will rotate the entire space based on shared labels. Now, what that means is, let's say in time 1 you have 5 people, and in time 2 you have 10 people, of which 5 are from the original point in time. I will rotate based on what is shared between both time points so that you can actually have matrices of different sizes. There's no other software out there that currently can do this. So what normally people would do is reduce down to a common set of labels across all time. I don't have that requirement, and therefore you can have much more complicated data sets. I also provide a solution called optimal choice. Now, in some cases, you're going to split your data based on gender or an age group. And again, you need to compare the data sets using this rotation. Optimal choice looks for the most common set of concepts shared between two spaces and rotates those two spaces to each other. The difference being is instead of going from point in time to point in time, it looks for what it will find is the best solution among all possible solutions. Again, this just gives you a better and accurate data set visualization in the end, and it's just another way of doing it. I have a time series solution for longitudinal, as I said. Scaling. Okay, this is important. Scaling is something that's normally done in every Procrustes rotation. What it does is it also looks to see if it can expand or contract your space to fit the other space you're rotating to. I have had instances with researchers where scaling is not something they want to do because the scale difference is actually representing something of the data. So we made the scaling optional, which is again another feature in our Procrustes rotation, so that you can do it or not do it depending on your needs. So this is just a summary of the difference between the two kinds of rotation. And again, this was the hardest part of the test and the most confusing. We can actually start to get to some of the fun graphics. Now what you're looking at here is just a snapshot of a space that was generated, one with rotation, one without. You'll notice that the large white ball is on the left without rotation and on the right with rotation. What this is actually just here to show you is that this is an axis flip. This is a situation where the MDS coordinates flipped on the x-axis. And so what you think is a major difference in your data is actually a byproduct of the MDS. What I'm about to show you is a series of snapshots taken of a time series without being rotated. Okay, pay careful attention when you watch to how the graphic is moving. I'm going to then show you one with rotation so you can actually see the difference. As you might notice, there's a lot of flipping back and forth across the axis. This is actually a product of the MDS algorithm and the way it runs. If you look at the same data set rotated, you will notice that the white ball stays more towards the right side. It never flips the axis. This is the true change that's occurring in the data without that MDS rotation issue in the middle of it. This is why I explained all of the rotation stuff so you know why it's there and how it affects your data. Okay, one of the neat features that the program will also do is calculate centralities for you. For those of you that know social network analysis and network analysis, there are a series of centrality measures that you can find in many programs. I use the Java Universal Network Graph method, which is publicly available and used widely, to create the binary and weighted sum and average distance centrality, which gives you 4 values, binary weighted betweenness, which is 2 values, binary and weighted closeness, which is another 2 values, and then finally, I give you 4 values of degree centrality, which I calculate internally because it's faster than using Jung under the case of what I've done. These centralities, when this program generates your final outputs, will be available for you to look at, and you can actually plug them in as features in your graphics at some point if you want them to reflect something in your outputs and your visualization. Now, matrix to coordinates is a very simple application. What you're seeing is a snapshot of it with some data, and the data happened to be for George Barnett. What you'll notice is that there are a couple menus at the top. A window to tell you what data you have loaded, and that is basically it. The project menu lets you load, save, and set up new projects. It's also where the run option is to run your coordinate generation. The input files menu will let you add, remove, and reorder your input files. Now, input files can be either tab delimited, comma delimited, Microsoft Excel 97 and older files, or the more recent Microsoft Excel XLSX files, which are XML. I can read all of them, and you can also do pairs, or you can do matrices as your inputs. The configuration menu will provide you the controls for how you're going to rotate, what kind of outputs you want to generate, and the centrality calculations you want to do. Of course, help and documentation are available. I highly recommend reading the documentation. It'll give you great insight into the various options. The input file, again, can be delimited, XLS or XLX. It's either relation pairs or it's a relation matrix. And you can actually do multiple files with multiple spreadsheets in them, and it will read each spreadsheet as an individual data set. What I tried to do is give the largest range of input methods possible while keeping it as simple and easy as possible to use. Outputs are very simple. They are always in XLSX Microsoft files, and I create a series of them, including a coordinate file, which will contain all of your coordinates for each point in time or for each data set, depending on how you're doing rotation. And the coordinates generated will either be 6 for visual purposes or the full data set if that's what you elect. Time series files actually present both the coordinate and the centrality measures in a way that you can actually look at them across data sets for each of your objects. This is really important because what you can use it for is looking at the time series data for things like SPSS or MATLAB or anything else where you can actually do certain other calculations that I don't do. We also create the ETV data file. You can actually generate a default data file that can immediately be read into the visualizer. It'll provide the coordinates in there. It'll also provide anything above the third coordinate is colored, which you'll see later in one of the examples. And it is the default file you're going to use when you go to set up your visualization to add other data into it. We'll talk more about the contents of this file later when I get into the visualizer. Finally, you can also generate a structurally equivalent paired data file. This is just the structural equivalence matrix that it generates to generate the coordinates. If you're interested in looking at it, it also will generate an error file. Now, something to note is that when you normally do classical multidimensional scaling, the number of dimensions you can generate is always equal to the number of objects you have. So if you have 500 objects, you can actually generate 500 dimensions of coordinates, and will be the most concrete distance that represents the structural equivalence distance. When you only look at the first three dimensions, every other dimension that occurs after is missing information. What I do is I use coordinate data and I compare it to the SE matrix to determine the difference in the final distances. So if the distance between two objects is 5 units in the coordinates, but it's supposed to be 5.8 units in the actual structural equivalence matrix, you have a 0.8 error rate. And what this file will contain is all the errors summed so that you can see what the different errors were as a function of your coordinates and determine your error rates. I've used the error rates as the object size in the visualization to show, in the case of a sphere, that it's somewhere within the sphere, here plus or minus because of the error rate. Okay, when you go to do the outputs through the program, it's going to ask you where you want to put them. It creates a directory called N2C output that it puts everything in. That way, it keeps it separate from your data and doesn't overwrite any old files or things you want to keep. And finally, each file will be in a spreadsheet form, and all the information in the data set will be found within these files. I will show you briefly later, if we have time, what some of these files look like. Okay, before I continue and start to get into the visual program, does anyone have any questions about matrix coordinates?
Hi, Ben, this is Yun. I have a quick question. So essentially, this M2C, you can generate initial coordinates for the network. Can I manually specify the coordinates? For example, I want to group a certain set of nodes together because they are in the same. And then whether I can manually put those coordinates and then display the set of nodes in a certain space.
Yes, you can. The input file for the visualizer is, again, going to be a Microsoft Excel file. You can actually manipulate that file to have anything you want in it. The matrix to coordinates program is there to give you a way of getting coordinates if you don't have one already. If you have a means of generating coordinates, feel free to use whatever coordinates you want. I will show you soon what the input file looks like, and you'll see it's real easy to put them in.
Okay, thank you.
Does anyone else have any questions? Okay, then I will continue. So now we're going to talk about the visualizer, the thing that has really brought you here. This visualizer is also an intonator. It will, as stated earlier, allow you to listen to your data. We will listen to data shortly. Now, the interface consists of 5 windows. What you're looking at now is a snapshot of the main window where you're going to be able to rotate the image with your mouse, and you're going to zoom in and out, and you're going to be able to look at different things. At the top is a menu that allows you to take snapshots and to launch the configuration windows, which are the remaining windows. The first window is the environment configuration window, and this window is what allows you to do global settings, including colors. You can scale your objects, scale the font size, change how fast you move around the space, control the quality of the visualization, and you can also change your edge settings, which I'll show you later, so that you only display certain edges of a given string. Data set interface is where you're going to basically do all your data loading and where you're going to have global data settings like the color for the file, whether edges are visible, and which data is visible out of the entire set. The next window is your object list. This provides you access to the individual objects of the data sets you've loaded. It is a master list of all the objects, so it'll list any objects that appear across all data sets rather than just single data sets. Here you can also do controls about which shapes are visible, clustering, because there's this new feature, which I'll show you later, that allows you to look at ego clusters, and all sorts of other neat features. Finally, the animation and audio interface is going to provide for you the ability to control whether you're animating, in the case of time series data, and what you're able to hear with audio. I provide a lot of controls, which I'll show you again later, that allow you to really manipulate things and to disable features so that you can look at your data, which is initially very complex, and then start to drill it down to really cool, smaller sets. Okay. Now, as I said before, the input file is very simple. Okay, what you're seeing here is a Microsoft Excel snapshot containing the data file, and I highlighted in colors the areas so you can see what's there. Okay. The top bar, which is the green one, okay, is a fixed order of column labels. Now, I don't actually care what the label says, but what it is actually representative of is what data I expect to be there. Now, in the next version of the software, which I hope to release by the end of the year, you're going to have a lot more variability and control. But for right now, you have to leave it in the order that you see it, and all the columns have to have a value in them for that set of data. Okay. The yellow set is your attribute data. You'll notice that the first column is a label, and it contains, in this case, a name. Then I have the coordinates, the size of the object, all sorts of different parameters that you can specify for the audio and the visualization that you're going to eventually have. All of these are defined in the manual, which comes with the software, so you can look at the manual when you want to deal with each of the attributes in more detail. The blue area is where I put the relation pair data. You actually provide the entire list of pairs for your relations that I then visualize as edges in the graph. In this case, you can't see them all, but there's probably like 55,000 in this one data set. And as the purple line at the bottom shows, you actually can put multiple data sets in one file where each data set is a spreadsheet. This gives you the most amount of variability in how you're going to provide the data while keeping it as small as possible. By using the current Excel XLSX files, you no longer have the row and column limitations of the old Excel files, and you can actually go as big as you want. Some of my files have actually reached a gig in size, and they contain tons of data, and you'll see later what some of them can look like. Okay, now before I actually get into the physical software, I just wanted to go over the examples we're going to look at so that you have an idea of what the data is. The first example is Canadian migration. It comes from Barnett and Sung 2003, although we've continued to add to it. It represents 73 points in time quarterly from spring of '87 to spring of 2005. And what you're looking at will also be colored in this fashion so that you can see the change of seasons. Each object is sized as a function of the population of the province. When you listen to this data, it represents the mean migration overall. So higher pitch means more migration, lower pitch means less migration. And at some point, you're going to want to listen to, in fall of '96, a major change that's going to occur in the data when Nunavut, a new province, is added as a function of changing provincial borders in Canada. And again, this data is the amount of people migrating from one province to another. What we're looking at were patterns of who's moving where. Now, if you look at the two-dimensional version of this graphic for now, you'll notice there are clusters and patterns of clusters that form when we look at all the data simultaneously. I will show you this live in the application later, and we'll also look at it as a time series. And already you can derive some meaning out of this visualization just from the cluster. More to come. The next data set comes from Dr. James Fowler. It's currently the 93rd through the 109th Congress, which is 6 13 points in time. And what this data represented was the co-sponsorship of Senate bills among the different senators. I have colored them appropriately for the way the U.S. colors their senatorial parties. Republicans are red, Democrats are blue, Independents are yellow. The size of the object will represent the number of individual bills sponsored by a given senator. I used non-sphere shapes, which you'll see later, to represent party leaders. And then, this is very important. At one point during this animation, you're going to see a bunch of people swap sides and change colors. This is actually an event in which there were party changes, major party changes among the senators in Congress. And you'll see it visualized as a function of the color change, and they'll go from red and blue to purple as they're moving across. And finally, as we know, the current political climate in our country is very divided across the party line. You will witness as that party line develops through these Congresses, so keep an eye out for that. Okay, finally, for Sunbelt in 2011, in February, I am working on a series of data that covers 2001 to 2010, all of the abstract data. I am specifically looking right here at author relationships, okay, and their co-authorship of papers at the Sunbelt Conference. There were 3,406 distinct authors over 10 years, and as this chart will show you, the number of years that they publish for a given number of authors and how it accumulates as you decrease the number of years they publish. The data set we're going to look at, there are two of them. One of them covers all possible authors, and one of them will only cover those that have published 6 years, or rather 5 years or more. It makes a bit of a difference on the final graphic, and you can actually learn different things from both sets of data. Finally, real quick, this is just a brief bibliography of all the things I've had to use to make this software possible. And special thanks to everyone involved. And this will be available for you later to look at, and then leave that at the end. We do Q&A. Okay, so before I go to the actual software, which is, I know, the exciting part, I want to know if there are any questions. Okay, give me 1 second to go ahead.
No questions.
Okay, I'm going to see if I can get the application visible, and then we will continue. Give me 1 second. See what we can do. If you want, we can also take a 5-minute break if anyone needs to go to the bathroom or get a drink or anything while I get this set up.
Okay, so we'll have a 5 minutes break, and then you can take care. I'll be back on 2:40. A little bit more than.
All right,
5 minutes.
excellent.
Okay.
That's perfect.
Now it's on mute. You can. Okay, so Ben, are you ready? So we can get started?
I am ready.
Okay, yeah, we are back. Yeah.
Okay, well, you should have open on your screen a Microsoft Excel file, which is the data file that I'm currently looking at.
Yes, we can
which
see
is
it.
the first. Okay, this is the first example of the Canadian migration. And so just to answer your earlier question, you'll notice right here where I'm highlighting, those are the actual coordinates for each of the objects in this data set. You can change those values to anything you want at any time. The file you're looking at now is the visualization file, and you can change the data in it at will. The files generated by matrix to coordinates will look like this, but they're only generated with the coordinates from matrix to coordinates embedded in them, so you have something you can look at right away in the visualizer. As before I mentioned, This data set is 73 points in time, and they're colored based on their season, the quarter that they're in. They also have audio values to them. All of these values were added after the matrix to coordinates were run. So this shows you the variability. Now, I added, while I was waiting for you guys, these spin values just to be able to show you what spin looks like. We don't actually use it very often at this time, but it's there, and they will not be in the data set that comes with the program, but I'm going to be showing it to you in a bit. So I just wanted to show you what this looked like before we move to the next step. Okay, I now have to share the other stuff, which I will do right now. Okay. And I'm getting an error because of the share. See what it does. Okay. Give me 1 second. I have to relaunch the program. And we will be up in a second. Okay. You should have on your screen a bunch of windows, a total of 5, which I am repositioning. If that's not the case, please let me know, and I will see what I did wrong.
Here we can see it, the 5 windows.
Okay, excellent. So as I said before, you have these 5 windows. Now, you'll notice when I'm clicking with my mouse, I can rotate, I can zoom in, I can move around. These are all features that come as mouse controls, and you also get keyboard controls as well. It's all covered in the manual, but as you can see, this is your visual space. This is where everything occurs. Now, I mentioned before the environment configurations as global settings. One of those settings, for example, is the font scale. Notice how I've increased the font so you can now read it, whereas earlier it was illegible. When you load your data, the space is expanded to the largest space that your data sets represent. And as such, the font will look off unless you properly scale it. That's what these worlds or environment configuration controls are for. You can slow and speed up how quickly the mouse reacts. Things like axis lines, if you're watching, you can see it increases the number of lines on your axis. You can go over here to rendering menu and change to a 3D axis or a circle axis. There are all these different options. I'm not going to go through every option today, but you should look through the manual because you'll see visibility allows you to control what you see and what isn't applied. Axis. You can choose different forms of coloring and which shapes you're seeing and all sorts of neat little things. All right, so our first data set, if you remember, I said was the Canadian migration data, which I am going to select right here. And it is now currently loading the data up. The more data you're loading, the slower it'll be, but as you can see, the data is listed. Here it is. This is each of the spreadsheets that exist in that one file. Now you'll notice nothing is displayed on the screen. By default, data when it's loaded is hidden because if too much data loads, it gets everything very slow and it makes it difficult to manipulate, and we want to start as clean as we can. Now, before I show you this data as a time series, I'm going to start by showing you this data as a static set of data. First thing I'm going to do is I'm going to show all the data sets with edges. Clearly, this is a mess. It's very difficult to see anything, but it gives you some perspective. I can also, in here, hide all data sets. I can select a group of data sets and show just the selected data sets. Wireframe will go to solid objects. As I said before, you can change the shape by forcing it. Pyramid, all of a sudden everything is a pyramid. When you specify your data for the input file, you can specify for each object its individual shape. The world configuration option actually overrides those values so that if you're confused by something in the data, you can simplify it a little bit. Okay. Now, if you remember before, we had some edges. I'm going to data set, top data set shows. Okay, so this is one data set with edges on it. Spin a little so you can see it better. Now, before I mentioned that you can control which edges you see by their value. That's what this environment configuration, smallest and largest edges for. If you watch the screen, as I change the value, edges disappear. You can also go up to rendering and not show isolates, and it will only show those objects that have edges that meet the requirements. Okay. As I also said, you can look at ego clusters. Now, in the case of this data set, everybody's connected to everybody. So ego clusters aren't that useful here. When we look at the other data sets, ego clusters are going to play a huge role in the value that you gain from this program. Okay, so let's switch to a time series. We do that by telling it it's time series data. I'm going to show all data sets with edges, but because it's a time series, it will not display them all simultaneously. Rather, it's going to show them as an animation when we do that. Now, I had also mentioned this stuff has audio to it. We're going to enable our audio. Now, linear interpolation slices, this is important. The way it animates is it basically creates a linear slope between the 2 points in time, divides it by the number of frames it's going to show, and increments the change by that slope for the number of times it's going to need to do that, called the frames. This is known as linear interpolation slicing. The more slices you do, the slower the animation progresses. You will find that when you have large data sets, it's naturally slow because of the concentration. Yes?
Hi, this is Hugh. Could I ask a question?
Sure, go ahead.
Yeah, thanks. Before we move on to animation, suppose you could just take a second and interpret that graph for us, what it means to you, and what are some highlights of that graph?
Okay. Well, this graph, the honest truth is the edges don't give me much because it's completely connected. If I disable the edges, give me a second. Okay, if I disable the edges, first thing we have to note is remember that this is a representation of migration patterns. What the proximity of each object relates to is the closer two objects are, the more migration that's occurring between them. Okay, so you'll notice Quebec and Ontario are close, BC and Alberta are close, Manitoba and Sask are close. So those have a lot of migration between them. When I show you the animation, this will become much more pronounced. When we look at the Fowler data set, you'll see that the edges will also make a little bit more difference. But here they really don't. For this data set, the proximity is the most important piece. And when I animate it, again, you'll see it in much more detail. Does that help at all?
Thanks. And then eyes of the
it's their population for that problem. So bigger shapes have a larger population. Now, animate this and you see the motion, okay? It's going to be hard to see the size change. When we are done with the first animation, I'm going to go back and I'm going to disable the motion so you can see how the sizes change. All right, so let's start with the animation. And we'll start with this one, and I have my speaker from my computer near the phone. It is going to play the audio, and we will play with this audio feature a little bit more later. Now remember, proximity dictates the amount of migration. So the expanded space means less migration. Now one of the things we found in this data set was that During the spring and the summer, you saw the most amount of migration, which is why during those colors, which are green and red, everything's close to the center, and you see outgrowth during the winter and the fall because there's less motion during that time. Now, if you also look at the animation window, you'll notice there's a now playing text at the top that's telling you what data set you're looking at. Now, we've just run through the entire data set. If you want to hear the audio pattern a little better, we can speed it up, and I will not talk over this one. So, as you heard, there's a repetitive pattern in the data. The audio feature is mainly there as a request of Dr. George Barnett because he likes to listen to his data. It just so happened when we did this data set, if you listen to it with headphones and very carefully, you can discern a pattern within the pattern that we were then able to mathematically find, but we didn't even know to look for originally. And that pattern happens to be that the winter and the fall have a tendency to flip-flop in their amount of migration, such that one year winter will be a little bit more than fall, and the next year fall will be a little bit more than winter. But overall, the fall and the winter were always less motion than the spring and the summer. As I said before, you couldn't really see the size of the objects changing because of the motion. Now, if we look at the animation configuration window, you'll notice that you have all these options of what you're going to look at and what you're not. So if I disable the coordinates, I rewind and start the animation again, you'll notice it's no longer animating the coordinates. Now, something I haven't added yet that I need to, because I didn't realize, was it's supposed to actually hold them still in one spot. I will have to put that in the next version. That is a goof on my part. But we can, for example, also disable color or size. If I disable the color, rewind, you'll notice it only changes the color when it reaches the new data set. It doesn't do a graduated change in color, which we saw earlier. Okay, so this gives you a basic idea of what you can do. The earlier versions of this software are actually built around this data. That is why we had to do all these updates, because we've recently gotten much more complex and much better data. To show you that data, I'm going to start by clearing what we have, add a new data set. This is the James Fowler Senate data that I mentioned before. It just takes a little while to load because it's slightly larger than the Canadian migration. The Canadian migration had anywhere between 13 and 15 provinces at any given time. This has anywhere from 100 to 103 senators at any given time. Now you'll notice that in our first data set, we've got a very dichotomous but slightly mixed Senate. You've got some reds among blues, but there's a contingency and a large blue contingency representing our dual-party system. If I show all the data sets with edges, it's a mess. We will often refer to this as the spaghetti plate problem. That is where the edge controls again come in, because now I'm looking at the strongest edges, which means the people with the largest amount of co-sponsorship. If I disable, I can disable certain objects I have to figure out why that other isolate rendering is having a problem, but you can limit what you're visualizing by the edge strength. Now, another way to visually limit this is to look at the ego clusters. Now, if we do show selected ego clusters and we pick someone like R.C. Bird, okay, you'll notice what it's showing you are all the outlinks as a function of that individual. You could, in fact, select more than one individual and see how they both have their outward links, giving you their independent ego networks. You can also say you only want to look at shared objects, which are the people they both co-sponsored with. And you can also add something like the secondary edges, but as you add more data, you become more complex, which doesn't help you very much. All right, so let's start by getting ego clusters, and then we are going. Okay, so first, before we look at it with the edges, let me also show you by increasing the object scale. You'll notice that some of the objects are not spheres. Okay, now the easiest way for me to show you that is by going to visible shapes, spheres, and now only the non-sphere shapes are shown. These are representative of the party leaders. I happen to do it this way, and this is another way of breaking down the data, so if you want to show it with edges, now you can see the network specifically of the party leaders. Now the edges are colored as a function of the objects. Edges that are solid, like this blue one between Bird and Eastland, mean it's one directional. Actually, I apologize, in the case of this one, it's bidirectional. Here where you have red and blue merging with purple, that means the communication goes both ways. Another way to look at whether you have directed or symmetrical edges is if you go to the Edge menu in the dataset interface, you could say, don't show symmetrical edges. These happen to be symmetrical. You can also disable reflexive and directed edges. So let me get back to full display. Only show the non-edges. Now, I'm going to run this through the animation. This does not have usable audio, so it will be disabled. And I apologize, I'm going to start it again, but I'm going to slow it down. Okay, now what you're watching is the motion of the senators as a function of their relationships for their co-sponsorship of bills. Again, the closer two people are, the more similar their co-sponsorship patterns were. The size of the object represents the number of bills the individual sponsored. As you just saw, there was a period of growth in bill sponsorship, which we're seeing again. There was a merging of the parties as they started working together, and then all of a sudden they broke open again and they dichotomized. This is the 109th Congress, and as you can tell, there's very little crossover between the parties, which is exactly what we're seeing in today's political climate. I'm going to rewind it to the beginning. Another neat feature is you can actually step through the animation. Now, the slicing allows you to step through each one of the increments of the animation. And by constantly clicking the slicing, what you're seeing is the alternative is to do the next data set, which hops between data set without filling in the middle. Here's where you see we're bringing together. We're working together. We're increasing our, actually in this case, we decreased the amount of bills that were co-sponsored. All of a sudden, in the 98th Congress, we have a much larger amount of bills being sponsored, more legislation. We have a lot of crossover. We can reduce our object scale so that you can see it a little differently. Okay? And again, we're here is a great point because if memory serves me correct and I rewind, I'm looking for the purple. I'm not sure if I went past it. I may have gone past it. It may have been early. Okay, let me just look for it again. It's probably earlier. I'm not sure why I'm missing it, but in there somewhere is a party change. I will have to get back to it. I know we're almost out of time, so I just wanted to show you one last data set, and then we will go to Q&A. Okay, this data set is representative of the 150 most published co-authored people for Sunbelt papers. This is a great data set because I can actually utilize the edges. Now, this square box you see is actually a reflexive edge. For those that see reflexive, and then of course you've got the line between people. I'm going to show you specifically the ego cluster of Tom Snyder's and Philippa Patterson together, because what you're going to see here is the emergence of Philippa Patterson as a major contributor to the Sunbelt Conference. She attaches first to Tom Snyder's and then actually forms her own group. Here she is. And Gary Robbins is in there as well. And here they go. Now, if we step through it, and I will rewind and start in second conference, Philippa first appears working with Tom Snyder. Then she appears working with, I'm not sure who that is, it overlaps, but it's probably a student. Data set. Here she's working with Gary Robbins and Tom Snyder's on the same work. Here she has a student come in and she's working with Gary Robbins. Again, it keeps spreading, and if you change your perspective, she's working with this core group. And then all of a sudden, starting in Conference 29, you'll notice all of a sudden she is among her own major group. And although the group does shrink in the next year, you do have to realize that there's a limit to the number of authors being shown here. If we were to actually look at the data set that contains every possible author, this network is actually much larger and more distinctive. Pitch line sizes. If I were to undo the ego clusters and we rewind the animation, as you can see, as Sunbelt progresses, more people become involved. There's a lot of self-publication as well as cross-publication. Certain groups start to form. There's a major group that is obviously the Philippa Patterson, Tom Snyder's, and Gary Robbins. You'll see that that Carter Butts over here, he's a part of a major group in here. I believe in a previous set when we were in Europe, you can see the Philip Bonasich group, Tom Valente group, Kathleen Carley has a small group, and they're very distinctive, and they appear as a function of the data. All of this was generated through matrix to coordinates with regards to the coordinate system. So it's directly through all this application. And again, this is all part of what this visualization does. There's so many options for things you can do, both audio and video, that I highly recommend reading. And again, I'm always available for questions. And I guess that's it, because I know I'm running a little long. Does anyone have any questions?
Hi. Could you explain a little bit about what a data set requires in order to have audio enabled? I know the first data set had audio, and you said the second wasn't prepared for it. Is there like a...
Well, all right. The audio is actually a characteristic in the data. I am going to bring up a Excel spreadsheet with the data again so I can show you, and I'll show you where the audio goes. Get the data set up. Share this screen. Here we go. Okay, can you see the data display? It should be showing an Excel
No, I can
spreadsheet.
see it. Yeah.
Is it there?
It's gone. Okay, now it is. Yeah.
Okay, it's just delayed a little. Okay. Can you see where my mouse is moving? Selecting things?
Yes.
Okay. These columns are the audio columns for your data. Each of these can be specified with a numerical value. You generate the value from your data however you want. I don't currently, in the matrix coordinates, apply it to the audio because it's really something you have to decide whether you're going to get value out of or not. The note is basically a integer value between 0 and I believe 127 that represents one of the many MIDI notes. Instrument is where you'll specify the instrument ID number you want to use, and the manual contains a list of all the instruments and their ID numbers so you can pick what you need. The channel, basically most audio these days has anywhere from 4 to 16 channels. What I use that for is you can split your data on different channels so that, for example, when dealing with the Republicans, the Fowler data set, I could say channel 0 is the Republicans, channel 1 is the Democrats, and channel 2 is independents. And then when you're playing with the audio controls in the visualization software, you can tell it only play the audio from a given channel. This way, when you're listening, you can break it down. Velocity has to do with volume, and beats have to do with the number of beats it's going to generate between time slices. I don't have the time to show you right now, but if you play with the audio interface, you can actually have it generate multiple tones between time points and even graduate the tones so that it sounds like something different. Again, the manual will give you far more detail about how to specify these values, but this is where you put them. And it's really that simple. Just stick them in and then listen to your data.
Thank you.
Are there any other questions?
I have a question. What would the performance look like if the size get really large?
What I have learned painstakingly is that your graphics card is going to have a larger influence in the long term than anything else. On a very, very massive data set, the calculation time for getting the data ready for visualization was about 21 milliseconds. But the actual graphics visualization time took about 210 milliseconds, which becomes very noticeable when you're generating a data set at least every, you're trying to generate a data set every like 200 to 300 milliseconds, it starts to build a lag. The graphics card I'm using is a Quadro FX. It's probably about a $1,000 to $2,000 video card that has, I think, 190 graphic processors on it and either a gig or 2 gigs of RAM on it. It is my current bottleneck. I have a computer with 2 8-core CPUs and 24 gigs of RAM. They are not the problem. The cost of going to a video system to handle millions of nodes is too prohibitive for me. But for someone who can get the grant or get the technology, NVIDIA puts out a blade system that's actually dedicated to just graphics processing, and at that point, it's a limit on the hardware you have, because you can dedicate blades just to generating the data for the visualization at a much faster rate. There are ways that I can improve the performance, which I am looking into, but they involve things like multi-threaded data generation, and we start to get into quantum problems with timing on the data generation and the actual visualization. For now, I have not encountered a data set that's actually needed go to that level, but I'm hoping too soon.
Okay. So, when you are talking about the graphic cards, so does it mean that when your visualization animation is running, you have already made use of the GPU in the graphic card?
Yes, basically the way the graphics card is designed, when I send the command to it to generate the visualization, it handles everything, and it knows how to maximize its GPU's memory. As far as I can tell, every time I increase my data set, the milliseconds to generate the code for visualization doesn't change much. But the amount of time it takes to actually get it on the screen grows, which is the graphics card. I have not been able to really get deeper into it because I don't know how. I'm hoping over the next couple months to get in contact with people at NVIDIA and see if they will work with me and maybe even give me a grant of some of their equipment so we can really push the level of what's capable in the software. The software itself has no limits. It uses whatever's available. The only thing it doesn't do is specifically use multiple CPU cores or multiple CPUs. That's something I'm looking into doing, but I don't have the skill set for yet. But I know that with my machine, it cranks and it takes all the resources it can get its hands on. And it does push.
Okay, thank you.
Anybody else? Yep.
No, okay. So thank you, Ben, for the demo. It's interesting software, and then we probably will play with it using other data sets we have. And thank you again for.
Feel free to. Yeah, feel free to contact me if you're having any problems. Also, if you have any feature requests, you can let me know. You can email me, and I'll get right on them. Usually within 24 hours if I can. And also, I will be presenting this at Sunbelt, hopefully, assuming they accept my abstracts, this coming year in Florida, so I can more demonstration and answer your questions there. And again, go to my website. Everything's up there and ready to go, so you can download it as soon as you want.
Okay, thank you very much, and hope some of us will see.
Yes, and thank you again for having me.
Okay, thank you. Bye.
Bye-bye.